In this first mini lecture for Chapter 5, we'll talk once again about how we can use the structure of the periodic table to determine yet more useful information, such as which elements have similar properties and the periodic trends in those properties. In Chapter 4, we introduced electron configurations and the idea of core electrons and valence electrons. In this chapter, we note that the composition of the core and valence electrons in an element will be similar as you go down a column in the periodic table. While the energy level of the valence electrons will be different down a column, the number of electrons in each subshell will be the same for all elements in the same column. Since valence electrons are the ones involved in bonding, then the elements in a column with similar electron configurations will bond to other elements in similar ways and therefore behave similarly in chemical reactions. Similarities in electron configurations also lead to similarities in other properties. In the late 1800s, Dmitry Mendeleev was one of the first to arrange the known elements of his time by similarities in their known properties, creating one of the first versions of the periodic table as we know it today. In doing so, he also predicted that there were still other elements yet to be discovered based on empty spaces in his table where elements with similar properties should be located. Mendeleev was able to predict the atomic mass, melting point, density, and other properties of these undiscovered elements based on their position in his periodic table and the known properties of the elements nearby. In some cases, he accurately predicted properties for elements that wouldn't be discovered for another 70 years. If you want to hear more on this, you can watch this short video that I've linked to here on this slide. Over 100 years later, we now understand that the periodic trends in these properties are correlated with the number of protons and electrons in an element. The number of protons and the number of electrons increases by 1 as we step from left to right across the elements in a row. And there's an even larger increase in the number of protons and electrons as we step from element to element down a column. The electron-electron repulsion between electrons will increase as more electrons are added, and the positive charge of the nucleus will increase as more protons are added. So, for the periodic trend in atomic radius, first let's note that there are two approaches to determining atomic radius. In the van der Waals approach, the atoms of a large portion of a sample are assumed to be packed together without bonding so that the surface of each atom just touches its surrounding neighbors. Then the distance between the center of each atom can be calculated and divided by 2 to determine the radius of each atom. This method works well when the element does not like to form ionic or covalent bonds with itself, such as with metals or noble gases. In the covalent radius approach, the length of the covalent bond between two atoms of the same element is divided by 2 to give the covalent radius for each atom. This gives a smaller radius than with the van der Waals approach since the atoms will overlap when covalently bound together, decreasing the distance between them. Regardless, this method works well when the element is a nonmetal as they can form covalent bonds with themselves, as seen here with bromine. This chart shows the atomic radius of the elements as atomic number increases, going left to right across each row as we work our way down the periodic table. Looking at the trend in the noble gases, shown here in red, the size steadily increases. The same is true for the alkali metals from the first column of the periodic table, shown here in blue. This steady increase in size down a column is due to adding large numbers of protons and electrons to the atom, which increases the nucleus size by a relatively small amount, but more importantly, increases the size of space occupied by the electrons around the nucleus by a large amount. Remember that the space occupied by the electrons around the nucleus is what makes up most of the size of the atom. Remember that each row of the table begins a new outer shell of valence electrons that are farther away from the nucleus than the electrons in the core. This increasing number of inner core electrons increases the shielding of the new outer valence electrons from the nucleus, decreasing the effective nuclear charge of the protons in the nucleus. With decreasing effective nuclear charge, the outer valence electrons are not held as tightly to the nucleus as they don't feel as much pull from the nucleus, which makes them spread out further away from the nucleus and drastically increases the size of the atom. However, across a row, the trend is more complicated as we see it generally decreases as we go from left to right across a row. Notice this repeating pattern from the blue alkali metal at the start of each row to the red noble gas at the end of each row. There are some odd exceptions to this trend once we hit the transition elements in the D block of the periodic table, but don't worry about these exceptions right now, as they are the topic of another upper-level chem course. However, we can explain this general decreasing trend in atomic size across the row as each element adds another electron and proton. The new proton increases the positive nuclear charge, but the new electron only causes a small increase in electron-electron repulsion and shielding because it goes into the same energy level as the valence electrons that are already present. So, since the electron-electron repulsion and shielding is staying relatively the same across the row, and the positive nuclear charge is steadily increasing, then the effective nuclear charge that the valence electrons feel is steadily increasing as well, as there isn't a significant increase in shielding. This means the core electrons and the valence electrons will all feel a stronger pull from the nucleus, causing them to move closer to the nucleus and shrinking the size of the atom, despite the fact that we are adding more mass and more electrons to the atom. This decrease in size across the row can be a bit non-intuitive unless you truly understand this trend in effective nuclear charge and shielding and its effect on size. This slide shows the trend in atomic size as heights of the elements within this table, and it includes the radius for each element listed below the element symbol. Note the smallest element in the table is helium in the upper right corner, and the largest element in this abbreviated version of the table is rubidium in the lower left corner. So this matches this overall diagonal trend that we see of the size increasing as we go diagonally from right to left and from top down. When considering ions of elements, anions add extra electrons without adding protons. Therefore, the extra electrons increase the electron-electron repulsions and shielding so that the effective nuclear charge decreases by a small amount. This leads to an increase in the size of the atom. So, as we see in this chart, anions will be larger than their neutral atoms. For cations, removing electrons without changing the number of protons leads to an increase in the effective nuclear charge, since there are fewer electron-electron repulsions and decreased shielding. So the atom gets smaller as the electrons are now held much closer to the nucleus. For anions and cations from the same column and with the same charge, the ion size generally increases down the column just like the atomic size, and for the same reasons. Now, any cation of an element is generally smaller than an anion of any other element, except when comparing ions from the extreme corners of the periodic table, as mentioned in this statement. Finally, when comparing ions of different elements that are isoelectronic, which means they have the same electron configuration, the larger the positive charge, the smaller the cation will be, and the larger the negative charge, the larger the anion will be, as seen in this list of ions below. This is due to the consideration of effective nuclear charge and the fact that all the ions have the same amount of electron-electron repulsions and shielding since they have the same number of electrons. The highly negatively charged anions have the fewest protons, so the electrons feel a lower effective nuclear charge, while the highly positively charged cations have the most protons, so the electrons feel a higher effective nuclear charge and are held tighter to the nucleus. The next property is ionization energy, the energy required to remove an electron from a gaseous atom or ion. Similar to the binding energy or work function that we saw in Chapter 4. It represents the energy needed to promote an electron in the atom past the n equals infinity energy level, thereby separating it from the positive attraction of the protons in the nucleus and ejecting the electron from the atom. For metals that want to give away their valence electrons, the ionization energy is related to the stability of the noble gas configuration that the metal wants to achieve. Therefore, it is relatively easy to remove the first and second electrons from a metal in the second column of the periodic table, like magnesium, because these outer shell valence electrons don't feel a particularly large effective nuclear energy due to all the shielding from the inner core electrons. And the outermost electrons are at high levels in the energy level structure of the atom, so it doesn't require as much energy to get them to eject. The removal of the first electron will be easiest, require the least amount of energy, and the removal of the second electron will be a little harder due to the increased effective nuclear charge after removing the first electron. However, it will be very hard to remove core electrons, and the third ionization energy is incredibly large compared to the first two. We can really see this in the chart on the right here, as these first two blocks represent the first two ionization energies, and then we have a huge jump when we go to the third ionization energy. This is because removing the first core electron will take away the stable noble gas configuration of electrons, and the effective nuclear charge will be much higher after removal of the two valence electrons. Finally, note that for sodium, the large jump in ionization energy happens between the first and second ionization energies because sodium only has one valence electron. So all elements will see a large increase in the ionization energy for core electrons compared to valence electrons. This chart plots the trends in the first ionization energy for all elements in the periodic table. Note that the ionization energy increases across a row since the effective nuclear charge also increases across a row, making it harder to remove that first electron. This also makes sense for the nonmetals at the end of the row and the noble gases, as they want to achieve a noble gas configuration. And so for nonmetals, we need to gain electrons instead of lose them. And for noble gases, we're happy with the configuration we have. Down a column, the ionization energy decreases as the valence electrons in large atoms get farther and farther away from the nucleus and experience lower effective nuclear charge, so it becomes easier to remove them. Note that this trend is exactly opposite of atomic size, as large atoms would be expected to have smaller ionization energies, and smaller atoms would be expected to have larger ionization energies. And all of this is based on that proximity of these outermost valence electrons that are going to be removed, their proximity to the nucleus, and the effective nuclear charge of the nucleus. The last property is electron affinity, which is sort of the opposite of ionization energy, except this time we consider how the energy of a free electron changes when it is added to the electron structure of the atom. These values are usually given as negative values because a free electron is in a very high energy state on its own, but when it is added to the atom, it feels the stabilizing attraction up to the positively charged nucleus and actually releases energy as it reaches a lower energy state within the atom. A release of energy is typically given a negative value to indicate that the energy is released and not gained. Negative values are typically expected for the elements that form anions, such as nonmetals, as they are typically seeking to gain electrons in order to complete their valence shell. We also expect the magnitude of the electron affinity to increase or become more negative as the size of the atom decreases, because the electron will feel a stronger effective nuclear charge from the nucleus and be more stabilized in energy, therefore releasing more energy. Although, it's worth noting that fluorine has a 2p orbital that this electron is going to go into, and it's so small that the extra electron-electron repulsion from pairing up electrons in this tiny orbital means there is less stabilization than you would typically expect. So the electron affinity for fluorine is not as large of a negative value as we would normally expect. This table shows the electron affinities for all the main group elements. In general, the values get more negative, larger, as we move across a row, but note that the second column of metals has positive values indicating that adding an electron to these elements is highly unfavorable and would actually require energy since the effective nuclear charge in these elements is not strong enough to stabilize the electron significantly. Also, the noble gases have positive values as they have filled valence shells already, and they don't want to gain any additional electrons as they would be going into the next energy level, which would be highly shielded by the inner core electrons and therefore less stabilizing. The values also become less negative or smaller as we move down a column because the effective nuclear charge is decreased and the electrons would be going into orbitals that are farther away from the nucleus, so less stabilization of the electron means less energy released. This concludes the first mini lecture for Chapter 5. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza, and I'll also take questions on this material during one of our virtual class meetings, during which time we will focus more on problem solving for concepts in this chapter.